So how did everybody feel that the homework went on the shortened 3-problem homework? No major complaints. Are there any questions about any of them?
I think the last question was like, it's similar to the example on a book. It's like 2-layer barotropic one.
Yeah.
I don't know what's the difference between them.
So the difference is in the continuous case, you also get the surface conditions.
No, it's like the textbook was the barotropic one, and then the homework was the quasi-geostrophic.
Yes.
And they're both 2-layer questions.
Yeah. So yes. Anna came in and asked me questions about this yesterday too. So I had the feeling this one was coming.
Oh, sorry, it's the Baroclinic on the textbook.
Right. So the 2-layer has a baroclinic and a barotropic potentially also, but not in the Eady problem. So it turns out it's just the baroclinic part that you have to worry about. And that's because you don't get a barotropic instability unless there's a horizontal change in the potential vorticity. So, yeah. Anyway. Let's go back to the one that's in the book, which is, I'm looking ahead to chapter 10. Okay. Let's see, a little bigger. Is that big enough? Can everybody see? Right. So you have 2 layers, right? So when you make the equivalent of this equation, you have an upper layer PV and a lower layer PV, and then you have to go through and make 2 versions of this essentially. Instead of having the buoyancy equation and this, you have 2 PV equations instead of this equation and this equation. Does that make sense to everybody? And then when you go through, so you're basically following the same machinery to try and get to a statement that looks like this, but you have a sum over the 2 layers essentially. So then you say the PV either has to be a different sign in the upper layer and the lower layer is the way that it ends up being, or that the interface between piece that comes in there gives you a contribution. Yeah.
I have a question about 8.94. I don't understand
where this comes from.
Yeah.
Okay, so let's see if we can do it now. All right, so V times Q, average, is the average of V. So what's Q? It's del squared of stream function, or it's dV dx minus du dy, right? I don't even remember whether the beta y term is in there, but and then we'll see what happens to it. And then we have d by dz f on n squared buoyancy, right? Okay, so this one to this one gives us that term. That's not surprising, right? This to this. So we have v dx minus v du dy plus v times f average plus d by dz, d by dz f on n squared. But there's an interesting point. How does the v get inside? Is that the part you're worried about?
Yeah.
What happens to the ddz of v? Well, what happens to this one? Let's deal with that. It's the partial derivative of v squared, and then if we were integrating an x, if the average involved an x average, this one would be gone. This one is just that one, because equals, I can put the y derivative on the u, and I get this term, which is the same as this term. But if I put the y derivative on the v, what do I get? dv dy. Right, so I have to, that's the other one. But then I have incompressibility on this, so that's equal to v du dy minus u du dx, and then this one vanishes for the same reason this one did. So I can pull the v inside for this term, which is this one. Yeah?
But in the, so you're using the incompressibility, but only in the 2D case?
Only in the 2D case, because
This is the perturbation.
yes, but so
Oh, but
it's
still
still a leading order, this one. So the W correction, I guess there's an ageostrophic part which isn't in there. So you could.
Or maybe because we assume that the perturbation is only the x and y plane and zeta.
Well, when I did from here to here, I could have also said u dw dz. And then this one is small because W is small, I guess, compared to this one. So it's the second, yes, there is conceivably an ageostrophic piece here, but this is, there's no reason why we don't have the geostrophic transport in this one. So the bigger term in the V is the one we want. We're really thinking of the geostrophic velocity at vector Q. Does that make sense? Because if I go back to the equation this came from, this is the poleward eddy flux of potential vorticity in what equation? In this equation. So it's just the geostrophic advection that we're worried about.
Even if Q is not up. Oh, okay, no, yeah. Okay.
Does that make sense?
Yeah.
So in the QG system,
Yeah,
this is the only one we have to worry about. I could have put a G there. That would have been okay.
I was confused with the background. So that is
Yes, this is yeah. Does that make sense? Although we still have the problem with how this V gets inside of there. Oh yeah, all right. How does the V get inside? I have another relationship that's sort of like using incompressibility here that helps with that. What's ddz of V? Thermal wind, so I can make F cross U equals gradient of B, and then I suspect the gradient of B part kills the other term. So if I bring the V inside, I get a term like this times, so it'd be which, don't need an F there, which equals 1 over n squared B 1 over n squared b grad b, and then you pull that one inside of there, and it'll go away for the same reason that this one did. Does that make sense, everybody? Sort of. Yeah, I mean, that's the whole game. I mean, this is the whole. The problem with these results is that these are considerably simplified from the one that you start with, and you have to play all these funny games of switching things inside and outside derivatives, and then convince yourself that all of the differences go away. So I guess in the perspective of doing it for a homework problem, you know what the answer is, so you know where you're going, and I don't think Valis has made a mistake in this formula, but proving it to yourself is a bit tricky in those intermediate steps. Frequently, I find, though, this style of doing it is much harder than differentiating this and going backwards. So this has got a v in it, so I'm going to take dy of u and figure out, show me that actually ends up being the PV. Like, so we kind of work from both ends to the middle. Because integration by parts it takes a lot of practice before you start seeing them. It's much easier to do product rule. Like, it's easier to see it going forward rather than backward. So does that answer your question, Anna? Okay.
Because I was,
What?
I was taking the VB mean, second part equal to 0, but I was thinking about that because of the equation above.
This being?
Yeah, because it goes to 0 when, because by.
So this one goes to 0.
Yeah, and.
But maybe not this one.
No, okay, but I have to
Yeah.
think more about that. Okay.
Yeah.
No, but it's not, okay.
But this formula gets discussed an awful lot in the parameterization of geostrophic eddies, because these two terms appear in like this equation and this equation, or not this equation, but the momentum equation. And this is the one you want if you wanted to parameterize the PV equation. And so there's a lot of discussion about this versus that. And one of the really weird things, a disturbingly weird thing, is these are both inside of derivatives and this one's not. So if we think of the flux of something coming into and out of a box, the flux of momentum, momentum's conserved starting and ending, because it's inside of a divergence of a flux. So in the momentum equation, it's conserved. And the buoyancy equation also, you can think of it as a transport of buoyancy, not the variance equation, but the buoyancy equation. So it's a divergence of a flux of buoyancy. But this oddball thing is not the divergence of the PV flux. It's just the PV flux. So in the parameterized momentum equation, instead of a divergence of momentum that looks like this, you end up with just a raw PV flux, which is extremely weird because it doesn't have it doesn't naturally go to boundary conditions or anything. So the magnitude of the PV flux, not just the PV flux divergence, appears in the momentum equation because of this relationship, which is super weird and mysterious and whatever. And people get very concerned about it and think deep thoughts about it, but the simple thing to remember is, don't forget that the PV is already a derivative. It's got a derivative built in it because it was built from the vorticity equation. So it's already, all of the symmetries of the space have to be built in already at the level where you've even formed a PV equation. So you can't get confused, even though it looks like you might. Which is one of the big mistakes in thinking about PV. Oh, I wanted to talk about the paper, speaking of PV, so for the next homework, the last problem is to give me a proposal for what you'd like to write the final paper on. And so I put up the final paper assignment, which I can pull up. And And the final paper assignment is, it's a short paper, like a GRL length paper. Okay, so this is not a long thing. So the basic gist of what you're going to do is you have to at least use 2 papers. You can't just review 1 paper. You have to review 2 papers. So you have to at least synthesize something. You can use many more if you're interested, and some of the problems actually lend themselves to a light treatment of a variety of papers rather than deep in 2. So it kind of depends on what your topic is. But I guess what I'd like you to put on the homework for now is just a short proposal, which just, you thought a little bit about what you'd like to do, you've identified the papers you want to talk about, you have a kind of working title, you have 1 to 3 things you're going to be thinking about looking at those papers by just, basically you're looking at the papers and reading the abstracts and thinking, what would I like to compare if I was comparing these 2 papers? And then you might identify some other papers that might be helpful, even though those aren't the prime ones, or like which figures in those papers you'd like to reproduce in your paper and that kind of thing. The final paper, you don't have to do original research. That's not what this assignment is. It's just giving you an opportunity to engage with some of the papers in the recent literature that are touching on the same topics we're talking about in class, and trying to either link one paper to the textbook, or paper versus paper, or even textbook versus textbook, so some of the topics, so I gave you a bunch of different topics that you could think about. So on submesoscales, you can talk about symmetric instability versus geostrophic instability. Bottom submesoscales, bottom boundary layer versus surface boundary layer. You can talk to G-High about that. Mixing versus restratification in the bottom boundary layer versus the surface boundary layer. 1D mixing schemes. We're going to talk about different ways of doing 1D mixing, and Ching, a student who just graduated from my group, wrote a very nice paper comparing a lot of them, so you could just choose 2 out of his list of 12 and compare them. Submesoscale mixing interface, what is this? Oh, sorry, I should probably say submesoscale turbulence interface, but large scale turbulence, rotating stratified turbulence versus small scale turbulence. Here are just a mess of papers looking at simulations, trying to do them at the same time. You could pick a couple of those you wanted to discuss. Or atmospheric boundary layer versus ocean boundary layer. That's a totally solid one. You could just compare the Thorpe book to which we have the ocean turbulence book and we have an atmospheric turbulence book. You could just compare, like, what's different in those books between like what they describe happening in the atmosphere, what they describe happening in the ocean. So that would be a nice one. In scaling theory, here's a nice paper that's a recent paper on ocean mixing scaling versus the more general Monin and Obakov that we're going to talk about in class. And then the reason why I remembered to talk about this is PV. So there are a lot of interesting papers about PV and boundary layers. The most recent one being Abby's paper that she just submitted like in January. So if you wanted to try and think a little bit more about PV and how it works in boundary layers, that would be nice. And I'm sure Abby would appreciate getting feedback on her paper as well, which we just got the reviews for last night. So that's very cutting edge in that sense. And the good news is that the reviews look like it will be published, so it's not going to, there's just stuff to do. And then one other thing that I thought when I talked with Rosa about this was talking about some of the coupled modes of variability. So Chengping, she put up this nice list of a long variety of them. So they're, including the west feedback, but other, if wind changes the mixing in the mixing in the ocean changes the wind, then what happens? And so that PDF has a list of a bunch of those kind of coupled modes of boundary layer talking to boundary layer stuff, which would be worth thinking about. Or this recent one talks about how if you have an eddy in the ocean, it changes the wind stress and the heat fluxes into the ocean because of the eddy and damps the eddy. So there are some interesting linkages that are sort of like both fluids at once that might be fun to try and pull one of those out. So basically all I'm asking for in this one is to just start thinking about what you'd like to do. Maybe browse a couple of these links. I tried to give all these so that they're easy to find. Like you can just click on the links and get to the PDF of the paper pretty fast, or cut and paste them into Google Scholar. And so you can think about what you'd like to do. How this works for people who didn't take my ocean classes. So you give me this little piece, which is like less than a page, and I will give you feedback so that when you start working on the final paper, hopefully we just avoid some missteps, and I can give you a few more references to think about, or maybe this hypothesis is going to be too hard to prove. Don't take that one on. Or here's an easier hypothesis to replace it with that will be much easier to explain, kind of thing. It's supposed to make it easier for you to come to settling on a topic for the final paper. Does that make sense? Yeah.
Can we try things not included in?
Of course. These are examples. This is just like, I wanted to give you a sense of how some people can choose off. You might just choose off this list because one of these sounds interesting to you, especially if you don't know much about atmosphere and ocean boundary layers or the literature, because this is your first time taking GFT. These are easy targets. They will all work. They will be functional. But if you have something that's closer to your own research project or something that you'd like to bring in instead, sure, go for it. The only rule is you can't only look at one paper. You have to look at two. Or the paper and the textbook also counts. And so you're having to synthesize whatever's in the paper with whatever we've been talking about in class at a bare minimum. And the ones that work better is when you get a couple of papers that are talking about a few of the same ideas, and you're just able to isolate one of those ideas and explain it well. If that makes sense. Yeah.
Do you have recommendations on the interaction between ice and boundary layers?
Take a look at Chris's paper with Ellie Zipperman in 2016. That's a good place to start. There's a bunch of paper. So if you look at the papers that cite that paper, you'll find a bunch of others. Yeah, because those are really fun and very weird. And I mean, you've already looked at those and you're thinking about all those things. So you may want to talk about ice as well. That will be interesting. Does that make sense, everybody? Are there any questions about how that goes, or what's expected for the little blurb to go in the next homework? This is really not. I don't intend this to be a difficult thing to do or something that you're going to get judged on how well you do it. This is really a corrective measure so that the final paper is easier to get done by getting started thinking about it early and getting feedback from me before it goes on. Okay. All right. Other questions on the homework, or should we finish talking about the Eady problem and talk about why it's important for mixed layers? Yeah.
I still have a question about the boundary condition.
Mm-hmm.
I think in a shallow water system, usually we do not have a buoyancy flux through the bottom and top boundary. From the top and bottom and top boundary.
Bottom and top boundary.
In a shallow water system.
In the shallow water system, yeah, you don't.
But I mean, in the homework, we are dealing with a 2-layer shallow water system.
Yes.
So, I mean.
So how do you deal with that part?
Yeah, because I cannot get anything related to the boundary condition.
You don't. It doesn't appear in the 2-layer system.
Okay.
It's if you took the limit of stacking many layers, not 2, but like 100, you would see that in finite difference form, the PV condition. Let me pull it up. The necessary conditions for baroclinic instability. Oops. Come on. No, I don't want that. I want you to go. Oh. So in the limit of many, many layers. Sorry. Okay, so we have two classes of conditions for the continuous case. We have the PV one, but we also have the shear at the boundary. If you have many, many layers, the PV condition with the differences in stream function actually becomes a finite difference version of these. So there is a limit in the very, very many layers that you start to be, that this one and this one kind of merge into each other. In the continuous case, they are cleanly separated. There's a boundary condition on U, and then there's separately PV in the interior, because we have the buoyancy equation and we have the PV equation. But another way, I don't know if I want to even go into this level of detail, you can also do something called the Bretherton PV sheet idea, which is because the buoyancy appears in the PV, sorry, erase the V's and make this make sense. With this kind of an operation, the buoyancy and the PV are actually linked. If you take a delta function of PV, this is like a Green's function for that. So you can actually use, rather than a surface boundary condition on buoyancy, BDT equals 0, you can put a Dirac delta of potential vorticity there. Q equals delta of Z equals 0, I guess just Z, that ends up replacing that boundary condition. And then instead of this boundary condition, you have a boundary condition of Q equal B equals 0 at the surface. So the two equations, the way we write them in the QG system continuous form, are actually not that different, because the buoyancy and the PV are basically derivatives of each other. So setting a condition on buoyancy is like setting a Neumann condition on the PV, or the other way around. Setting a Neumann condition on the buoyancy is like setting a Dirichlet condition on the PV. And so digging into that piece of it, those two are actually interchangeable. So when you do it in a layered model, once you have lots of layers, the top layer starts to behave like the buoyancy part, and the jumps between the layers starts to behave like the PV part. Does that make sense? So it's sort of in the same way that the stacked shallow water is a finite difference approximation to the continuous shallow water. This is the same deal. Does that make sense? Or continuous boost nets, not continuous shallow water. Okay. All right. So, all right, it sounds like, let's talk a little bit more about the Eady problem. So the last piece of instability that I wanted to talk about is the Eady problem, which we touched on last time. It's a really simplified instability problem. It's the simplest instability problem. And the reason why it's helpful is because it's so simple. So F equals F naught. It's not on the beta plane. There's a flow, which is in one direction at the top and the other direction at the bottom, because there is a density gradient or a buoyancy gradient across the channel. And this gradient is infinite. It's just everywhere equal to the same thing. And sometimes you might also have stratification here as well, or not. I'm going to talk about why not. So I would, in this part, I would have an n squared, which is the stratification, which is dB average dz. And then I might also have an m squared, which is dB z y x dB bar dy. So when the people who mess around with this all the time, the background flow gets absorbed into n squared, which is the z derivative, and then because it's the next letter in the alphabet, m squared, which is the y derivative. And why they didn't lm n lm n? No, the one before. So just like z is after y, n is after m. Okay.
So they are the frequency of different directions?
This one's a frequency. This one is not a frequency. This is just a weird thing. It's just an analogy to this. This is a derivative of the buoyancy in one direction. This is the derivative of the buoyancy in a different direction. So this notation has latched on and is ridiculously confusing. But that's how people like to do it. Vallis smartly does not do this. But you will, if you go to a submesoscale session at AGU or something, people will be just slinging f squared, m squared, n squared, like playing games with this. And they write the potential vorticity with these n squareds and m squareds. It's really confusing. So, yes, but that's what I mean. Okay, so.
I'll ask you a quick question. So I know n is called the buoyancy frequency.
Mm-hmm.
How about m?
It's not called, it's called the buoyancy gradient, but they mean really the horizontal buoyancy gradient, and then n is the vertical buoyancy gradient. And it's even weirder that in this usage, they're really not even talking about the n itself. They're only talking about n squared. Anyway. Yes. And then, so these might be sloped if n is bigger than m. And in fact, you can figure out that the slope would, if the slope is, rise over run, this is dB dy over dB bar dz, which is m squared over n squared. Does that make sense, everybody? So this is why it's kind of a useful thing to think about, is this ratio, which looks dimensionless, and it is dimensionless when you write it this way, what tells you about the slope of those isorectangles. Okay. So what did we learn from geostrophic adjustment? If we started out without this thermal wind flow, what would happen? If we just had m squared, and say for simplicity no n squared and no shear. Would it be happy like that? That it has just dense stuff sitting next to light stuff? It wouldn't, because it would want to overturn, right? And so the dense stuff would start running over the light stuff, and this would start overturning. But then the Coriolis force would turn that, and we would get a geostrophic adjustment problem, so that this shear would naturally develop. So in some sense, this initial condition of the sheared is after the geostrophic adjustment has occurred. So it's in thermal wind balance to begin with. It would be just stable with that shear, because the Coriolis force on the shear is pushing back against the pressure gradient force from these buoyancy gradients. Does everybody understand why this is a reasonable initial condition? Like this would be a happy thing? Okay, so why is this a useful instability problem for the real world?
It's like if we consider the difference in the atmosphere between the equator and the pole.
Right, so we could have the pole and the equator, which is the buoyancy difference at the same altitude. We could have the Gulf Stream, which is warm on one side and cold on the other side. We could have a mixed layer, where the stratification increases rapidly below. And this is just talking about, so suppose you have warm stuff next to cold stuff, and then you mix really hard at night or in a big windstorm, you reset, and now you have a buoyancy gradient which has m squared but not n squared. So all of those cases are covered by this simple case. And the key part that makes this Eady is f is constant. Both of these are constant. And so if n squared is constant, it means the stratification is uniform. If m squared is constant, it means at all depths and all y values, we have the same b plus, b minus. And because of thermal wind, equals basically m squared, it means that the shear is also constant everywhere. Does that make sense to everybody? So the du dz in the vertical is constant everywhere in space, both in the vertical direction and the horizontal direction, and also in the long flow direction. And so there's just one parameter that explains that. And the stratification is uniform everywhere in space, and the Coriolis parameter is uniform everywhere in space. So it's sort of the simplest thermal wind balanced flow you could think of that might have an instability. Now let's go back to our necessary conditions. Where are our necessary conditions? Hidden them. Will our necessary conditions be satisfied by that initial condition? What's dq dy? What's the PV in this layer?
0.
It's 0. So, no, it doesn't change sign. In the interior, it just has one sign. It's just 0 everywhere. And if it's 0, it also can't be the opposite sign at the upper boundary, and it can't be the opposite sign at the lower boundary. So it's not condition 1, 2, or 3 that's satisfied. What about the udz is the same sign at the upper and lower boundaries? The udz is what? But it's also, if m squared is constant, it's constant everywhere in the domain. So it is the same sign at the upper and lower boundaries. It's in fact the same sign everywhere in the whole domain. So condition 4 is satisfied. So it is potentially unstable according to the Cherney-Stern-Pavlovsky criteria that we talked about last time. Okay? So what does the instability look like? Okay? So here's the PV, which is the Laplacian of the stream function, of the background flow, and the stretching part. So this one is 0 because the background flow is just everywhere the same and there are no horizontal derivatives. And this one is 0. Why? Or not, I should say this one is 0.
Vertical gradient of velocity is constant.
Yes, the vertical gradient. There is a linear part, but there's not a second derivative because everybody is just linear or constant. Okay, so the fact that q equals 0 makes the Eady problem a special case. Okay, fine. So then we go through a game and we plug in our usual e to the I kx minus ct. E to the I kx minus ct. So this perturbation Laplacian gives us a k squared part and a d by dy squared part. This perturbation buoyancy piece gives us a perturbation stream function, which looks almost the same. Notice that the deformation radius is hiding in here when you go through, that's coming from the n squared and the PV. And then this part is what? Oh, sorry, this is defined to be f naught lambda. So the velocity is just lambda times z, where z was 0 at the midpoint, so it's going this way. That's what he means by this lambda. So lambda z minus c times this thing equals 0. Okay, so how do I solve this equation? Can I make lambda z equal c everywhere? No. I might be able to make it happen at one depth, because c has to be constant in the vertical, because it's assumed to be a constant. But I can't make it happen at all depths. So I got to work on this hunk. And does everybody see, well maybe you don't, maybe you do, that this looks like a 3D dimensional Laplacian? It's got a ddx squared, it's got a ddy squared, it's got a ddz squared. So it's essentially, we're solving a three-dimensional Laplacian. Equals 0, which is easy to do. And so you go through that process, you get the 3D Laplacian, you get a constraint on what the potential values that C can take, and off you go. And you get a growing mode. And so like we've done before, I don't want to really go into the details of the algebra of how the instability is calculated, but it's the same kind of machinery we've been talking about, where you just are solving a linear problem. You get things like Laplacians, you do Fourier transforms, everything is fine. We can do a Fourier transform here in both directions for the perturbation field, because n squared and m squared are constant. So it's, you do a solution method, you get an answer. What do these growing instabilities look like? The growth rate, which is k times ci, has a particular peak at one particular location, and this is the zonal wave number measured in units of deformation radius. So on a scale that's slightly bigger than the deformation radius, you get the fastest growing thing. Does that make sense to everybody? So that's how big what it looks like is that this front starts to wiggle in such a way that the light stuff goes on top of the dense stuff. It starts to wiggle and tilt. And so there's both an imaginary part of C, so it's growing, and a real part of C. And that's what this complicated figure shows you both of. And there's a variation in the wiggles in the z direction, so they're not like columns like this, they're a little tilted. So they tilt, and that allows them to extract potential energy from the original front, because they're kind of working against this potential energy here by sliding it over and being out of phase. So on net, they end up reducing the potential energy. Okay, so, but let's look at some movies, because that's much more interesting. And you can go through the scales and see how big this is, and this tells you this is the most classic baroclinic instability, and the scale in the ocean for the full depth gives you features around, for the atmosphere around 1,000 kilometers, and for the ocean around 100 kilometers. So all the eddies in the ocean aren't too far from this scale. All the storms in the atmosphere aren't too far from this scale. So baroclinic instability looks like it might be storm scale in both fluids. And it satisfies the necessary conditions we've already talked about, and this gives you a little summary. So the one case that I want to talk about, which is relevant for the paper, is what if this is the mixed layer of the ocean? What if this is our boundary layer? There's turbulence, but suppose the turbulence stops and leaves this, what grows out of that? You can get instabilities in the mixed layer. This is showing growth rates for the mesoscale part, and also a part that's trapped in the mixed layer, the submesoscale mixed layer eddies. And oops, this is like an Eady problem, where this is warm on this side or light on this side, dense on the other side, except it's just an isolated front rather than uniform in space. And it was initially vertically mixed, so n squared was 0 to begin with, and you see over time it grows into these little eddies. So there's a baroclinic instability that's trapped in the mixed layer above the stratification, and it has a particular scale and stuff. if you go through the linear instability theory, the initial scale of those eddies is very well predicted by the Eady theory. So this is a lot of what, and these little creatures, if you look in sea surface temperature from satellites or in other complicated versions of ocean color, you can actually see them all around the world, and they have a good match to the scale. So we think this actually happens in the real world, even on the 1 kilometer scale. So the only thing that should maybe surprise you about that is how big do you think the Rossby number is at 1 kilometer? So remember, we did the geostrophic instability, the QG flow, and we had the Eady problem. And I told you that that was pretty easy to solve. Fine. What are the conditions for this to hold? The Rossby number is small, and the stratification, so the Froude number, or the 1 over the Richardson number, Froude number squared 1 over the Richardson. This was also small. So we had conditions basically on how big the vertical velocity part was. It had to be stratified and it had to be rotating in order to be QG. So the oddball thing about these little guys is that they're really, really small. So the Rossby number is actually, for those fronts that are in that figure, is more like 5 or 20. It's not less than 1. And also because they're living in the mix layer that was just mixed last night by cool convex air above, it's not stratified. So it's a weird beast, and that it is a weakly constrained by rotation, an unstratified flow that's behaving like a stratified rotating phenomenon that we know on larger scales. So that's sort of the essence of why the submesoscale is weird. And we will keep talking about it as we develop into thinking about how we put together turbulence and these kind of bigger things that are at the interface between the large rotating stratified flow of the large scale in the oceans and atmosphere versus the 3D turbulence of the very small scale. The submesoscale kind of lives in the middle. And sometimes it looks like one and sometimes it looks like the other. Yeah?
If this works for Rossby number, then does it work for the Hamilton?
No. So this is one of the weird, you can't, yeah, so it definitely violates QG. And if you look in great detail at this, it's in the full Boussinesq equations, not the QG approximation. You get multiple branches. Remember how we said the instability has like a part in that looks like the QG part, and then other parts that look like Kelvin-Helmholtz that are wave-like? So this is really the branch that looks like QG. But there are other instabilities that are on the wave-like parts that are all coexisting at this Rossby number. So the funny thing is that they don't blend. They still stay kind of distinct. So in this problem, in the Eady problem, under some circumstances, this one wins. This one's the fastest growing one. But under other circumstances, if the shear is stronger versus the amount of stratification, then the wave-like ones win. So you get all of them kind of in there together, neighbors. Yeah.
So why we find these submesoscale studies using the geostrophic
Why do we do it? Because that's what we understood this one well. So Eady did it in like the 1940s in the quasi-geostrophic system, and so we understood that problem well. And so when we, in the 1970s and 1980s, Peter Stone did the generalization, and he showed that the instabilities, even at large Rossby number, are kind of continuations of the small Rossby number phenomena. But that was only in linear instability, and then in the last 15 years, people have realized that actually even in the nonlinear simulations, these phenomena are important. So that branch continues all the way through, even though you might have, if you go back and read papers from the 90s, everyone says this is impossible, which is kind of fun. How do we explain that it exists? I don't know. It's sometimes, so QG is a funny system in that it seems to work qualitatively outside of its range of, it seems to still kind of work even when you break these rules. Not quantitatively. These eddies are actually a little bit larger than the QG theory predicts in the Boussinesq system, but they still have kind of the same dynamics. They're still unstable for the same reason. They still have, so a lot of features come over qualitatively, even though quantitatively it's a different phenomenon. People have been trying to come up with a mathematical theory that explains why what they call the quasi-balanced or the balanced modes that are the QG piece that extends into non-QG physics, why it still exists. No one's been able to do it. It's not, you can't prove from the Boussinesq equations that the balanced part exists outside of its regime of where it's the dominant one, but it seems to. Yeah, so it's a interesting forefront of what GFD is about at the moment. Okay, so next week we're going to talk about Chapter 10 of Alice, which is an introduction to turbulence. And for the homework that's due after spring break, we have the little blurb about the paper and then a few kind of introductory questions about turbulence that's of Alice and comes from Thorpe, which is the ocean turbulence book. And it's a very kind of hand-wavy discussion with lots of pictures to just kind of get you started on what ocean turbulence looks like. So that's where we'll be going for the next, until we get to that homework. And then we'll start talking about the atmospheric boundary layer, the ocean boundary layer for the remainder of the class. Makes sense, right? Okay, cool.